Right. Welcome back to CX1104. This is part 2. So part 2 meaning that we are in the second part of the semester after recess. So I'm Chung Eng Seong. You can Google me, and I've been teaching this course with Dr. Deepu since the first offering. In the last offering, it was by another pair of professors. So in this offering, I'm pairing up with Professor Deepu again. Now, so I guess if you first, what you should do is that you should go to your adventure and pick up all these slides. So I'll release the slides chapter by chapter along with the tutorial. So basically you'll see the slides and you'll get all these slides here. And I'm going to open up the first PDF. So I've just modified it. So it's 1st of October. Now, what we have is that I will now explain or share with you what we are going to do. We'll at least have one quiz which will happen on week 11's Monday, 25th of October. The detail will be provided later on. It will be, at this time slot. So on this time slot, you are then requested to go to the LTs again and then do the quiz, and the quiz will be like quiz 1. The coverage of the quiz will be chapter 6 and 7, which is orthogonality and least squares. So if you do, and then in the exam, it'll be chapter 6, 7 for question 3. Question 4 has QR decomposition, which belongs to least squares, and chapter 8. So this is the coverage. The coverage of the questions will be like the tutorial and quiz 2 that we have. So there'll be some MCQs and small workings. Now, if there's any questions at all, please do not hesitate to ping me. So what is chapter 6, 7, 8? Then you see 9. All right. So chapter 6 is what we're going to cover in this 1.5 weeks. So this is the title. We're talking about orthogonality and all these things. It'll be held in week 8 and 9. We'll take 3 hours of lectures and then this 2 hours of tutorial. So what happened is this. Basically, 2 hours of tutorial means 2 weeks, right? And 3 hours of lecture basically means 1.5 weeks. So within the first 3 weeks, we'll finish chapter 6 and 7. And that is why on the 25th of October, we would have the quiz. Now, so this is a very big chapter. So it takes about 6 hours. And after that, we have another 5 hours of eigenvalue and eigenvectors. So you see one question here, about 1.1 question here, and 0.9 question here in the exams. So you need to understand these 3 chapters. We will not examine you on singular value decomposition. I will record the lectures and you can watch it when you are free, but you will not be in the exams. Okay. Now, how will we conduct this course? Because I have pre-recorded all the YouTube videos of the lectures. You can watch them according to the schedule that was given just now, and the tutorials as well. So if I have done all this in the YouTube, then what is this for? It's in the lecture hours. So basically we'll summarize the lectures, we'll go through more detailed examples very, very slowly, and then we will do Q&A. So that's the purpose. And if there's no Q&A and if there's nothing to talk about, then everything is in the YouTube video anyway, then just go ahead and we'll have short hours of lectures. Right, where is YouTube lectures? If you do not know already, it is here. I guess I click here. Does it work? Yes. So if you click here, then it is, this is the playlist. Always visit the playlist. You'll see tutorial 1 to 4 previously I recorded. Then part 2 recordings is to lecture 6, lecture 7, and lecture 8. Sorry, chapter 6, chapter 7, and chapter 8. I would also put part 2 lectures 2021 Zoom. That means if the recordings I find are useful, I will put it here and then you can watch it. But if it is not useful, then those who come will be able to participate, but those who didn't will not get to watch this. So I'm populating tutorial 6, 7, and 8 now. I will update tutorial 8, but so take your time to watch tutorial 8. But 6 and 7 are updated. Okay, so I think I'll pause now. Right, so we had some questions, and the questions were, would the quiz be online or offline? And the answer is it will be on premise in NTU. So students who are not on premise, then we'll make alternative arrangement. That's one. Two is the number of videos to watch is totally dependent on you. And you can, if you understand the slides, you do not need to watch the video at all. Nobody will ask you to watch the video if you understand how to do the tutorials, the exams. Okay. Can you show the syllabus for the quizzes again? Okay, the syllabus for the quizzes. You can look at the syllabus for part 2. The syllabus for the quizzes is chapter 6 and 7, the orthogonality and least squares. So orthogonality and least squares will be covered in these 3 weeks. So in week 11, Monday, we would have the quiz for these 2 things. Okay. Does that answer your question, guys? Okay. Right. So we would are you still here? Where's my Zoom? Okay, sorry, guys. Okay, when will quiz 1 results be released? Right, you have to ask Professor Deepu. Okay, anything else? All right. Okay, so what I'm going to do now is, so I have gone through the quizzes and the exam matters. So now I will go through the length. I will go through the length of vectors, the definition of dot product. Okay, so I'll resume recording now. Okay, it is. Now, so send me a message anytime. It would, for the finals, it will cover from chapter 1 to chapter 8. So Darren asked for the finals. In the finals, all my part will be covered, all Professor Deepu's part is covered. Okay, right. The length except, yeah, Darren, except SVD. Okay, Darren. Okay. Right. So length of vectors. Now, when I did this as an undergraduate and when I studied vector, and then we always draw this. So for example, this we call it a vector, and we put the arrow little up, and then we said that this is a vector and this is the length of the vector. So the length is from here to here. And if we want to know the length of the vector, and of course, I mean, now this notation is not standard. I mean, but it says, let's get the length of the vector. And of course, in Pythagoras theorem, if this is x1 and this is x2, then basically the length of the vector is x1 square plus x2 square root. So every one of us know that. But in linear algebra, there are actually all these notations that also says that it's the length of a vector. So that's why it's confusing. So this guy is a parallel line, 2 parallel lines. and this is the length of vector. Some books put it as this, but this is not so standard because you may confuse with the absolute. Right, so the length of a vector, and then so let's put V equals to the matrix, the vector notation now, and then we say x1 element, x2 element, and then we say that it belongs to R2. Now, when we write it in this way, then V transpose is equals to x1, x2, and then V is of course the column vector x1, x2. And now what we can do is that since we know this is the Pythagoras theorem, and we want to get length of vector this way, then isn't it the same as writing V transpose V square root? So the length of the vector is also this way, and this way, and this way. So we have 3 ways to do it now. And then after that, you realize that there's another way to do it, which is this way. It is that writing the elements up, square root of x1 square plus x2 square root is the same as writing summation of xi square, I equals to 1 to 2 square root. So that's why there are so many ways to write it. And the last way to write it is v dot v, the dot product. So first we have to define the dot product first, and the dot product is this guy. So it is nothing but the length of A multiplied by the length of B and the angle theta between these two guys, between the two vectors A and B. Now, so what about A dot A, guys? Isn't it length of A, cosine? Now, since we are talking, if this is A and this is B, there is theta. But if this is A, and then we are actually doing A again, then the theta, the angle between them is 0 degrees, right? There's no difference between. So theta is cosine 0, cosine of 0 is 1. Therefore, this reduces to A dot A is length of A times length of A. So it is this notation. Now, we have already figured out that length of A is this guy. So it's equals to A dot A. What am I talking about? Square. Or we can do it this way. Okay. So square root of V A transpose A square. So that's why finally we have this notation over here for length of A. So there are many ways to write the length of a vector. Now, dot product in A levels, you learn this. And I was thinking, how do I motivate, or how would I want to motivate you to understand the dot product? So yesterday I was just thinking about it, and I went to watch this video. Math the Beautiful. So he's in Drexel University in the US, and he teaches very well. And here he explains from the principal concepts, and then why we are going to use the dot product for many things. Later on, you'll see that the dot product is going to be used for projection as well. So let me share with you basically what he says, and then you can watch this video. So I have a vector A, and he used this, I can't remember this symbol called gamma, I guess, A and B, and then the angle A between A and B vectors. So he used the traditional notation for vectors, which is that little arrow on top. And then this is the length. And then basically A dot B is equals to length of A times length of B cosine gamma. Now, and then he showed that the length of A is, from this first principle, if I have A dot A means A dot A here, so it's length of A times length of A cosine 0. So we have length of A square. But isn't it the same as A dot B square root? So that's why we get this. And he also motivate this, which is very important to us in next week's lecture, or this week's lecture later on Friday. It is a projection of A onto vector B. Okay, and finally the results comes out. A projection, and which is very, very surprising, which is this. This is A, the vector A. When we want to project vector A orthogonally onto vector B, orthogonally means we would pretend to be a very bright, a light source shining onto A, perpendicular to B, and the shadow of A cast onto B is the projection of A onto B. And we call this vector P. So what is the equation describing P? P is a vector in the same direction as B. So we have a B here. But its length is not B, it is something else. Its length is calculated by this funny looking equations, is A dot B divided by B dot B. And why is this so? He explains. And the surprising thing is that we have A here, we have gamma here, we have B here. But to describe P, gamma is thrown away. Length of A is thrown away. Length of B is thrown away. All we need is A dot B divided by B dot B. So which is a very surprising thing. So when I first listened to this, it was very, actually very illuminating that when we define A dot B this way, then it becomes useful for many, many things. Okay, so maybe since we have time, then I will play this part of the videos and we can pause and discuss this. Okay, so but if you have any questions now, please do not hesitate to stop me. Okay, so what I'm going to do is I'm going to change my sharing. Okay, let's see. Oh, Math the Beautiful. So when you Google Math the Beautiful for dot product, he explains dot product many times. So it is a very deep concept. He talks about it in a very generic sense, and he talks about it in a decomposition sense, but we are going to first watch the review of the dot product.
So as we've always done in lemma, in linear algebra, we start with geometric vectors. We start with geometric vectors. Study whatever it is that we want to study with respect to the geometric vectors. And then we notice a way to carry the analogy, the metaphor, to other spaces. So the same thing will happen here. So here's the definition. Well, let's draw them. Here is my vector A. Does this vector have a length? Yeah, if I pull out my tape measure, and I'll be able to measure it. Okay, it does have a length, I agree. And here's the vector B. Does B have a length? Yes. Okay. Can I measure the angle between them? What do you call the tool? The protractor, isn't it? Yeah, nobody uses it anymore.
Right.
Okay. So let me now write down the definition. The definition that all of you know, but I want you to take a fresh look at it. So A dot B, so this is called the dot product or the scalar product. It's called the dot product because you put a dot in between. We call it the scalar product because the result is a number. But I'm not yet calling it an inner product because inner product will be the linear algebra generalization of this concept.
Right. So sometimes you'll hear me use the term inner product, and like he said, the word inner product is the generalization for the dot product. The inner product takes vectors and perform some kind of what do you call that, operations on these two vectors. So you realize that dot product takes in two vectors, and later on you'll see that length takes in a single vector. So the dot product takes in two vectors and spit out a number. The length takes in a single vector and spit out a number. So there's some very subtle difference between them. Right.
Will is defined as the length of A times the length of B times the angle between them. Let's give it a name. Gamma, so it's neutral between alpha and beta, times cosine gamma.
You make yours louder. Thanks.
Right. So actually, if you follow his lectures, I'm going to jump now. So this is the interesting thing part when he talks about projection. So I'm going to take this opportunity to talk about projection and orthogonality
here,
now.
We have a vector B. I'm drawing it as horizontal just for convenience. And a vector A. Okay. And then let's find the geometric projection. And we'll call it P.
Right. The interesting thing about this diagram is that the dotted line is perpendicular to B, the vector P. And we call it orthogonal projection. If we just say projection, typically it is always orthogonal. So the word orthogonal means right angle or perpendicular. So the dotted line is perpendicular to P. And
just help me bring back my milk and admin shirts.
Okay, wait, can I ask, yeah, you have to turn off your mic, please. Otherwise, yeah, we could hear you. All right, so.
Okay, let's try to express P in terms of A and B and throw the kitchen sink at it, meaning you're allowed to use whatever you want, lengths, angles, whatever you want. You're allowed to use. All I'm requiring is that you express P in terms of A and B. So what direction does P point in?
Right. So when I first listened to this, right, I was very, very surprised. Very surprised because I didn't think of it that way, but he explained it very, very well. And he's going to tell you that the projection of A onto B in English basically means that how would A look like if we only have B to represent it? That's in English. And if we only have B to represent it, then of course the vector P, which is a projection of A onto B, must lie on B. So he's going to put a B here on the right hand side. But of course, it is not B exactly because we know it is a shorter version of B.
Yeah, it points in the direction of B. So whatever it is that we'll get will be proportional to B. So it'll be some number times B. You agree? Okay, step in the right direction. Okay, that's very nice. What number? Well, let's see. What is the length of P? So just answer that question. I see lots of volunteers for other things. You have the length of P? Yeah. Okay, gamma. So we'll call it gamma. So the length of P is the length of A times cosine of this angle. You agree with me? Remember that from projection from the right triangle, how sines and cosines work?
So basically you'll get A cosine gamma.
I feel like this topic very difficult.
Right? So you basically get A cosine gamma because it is nothing but the length of A, right? Cosine gamma, so you will get this scalar value. So you A, length A cosine gamma, not A. So it's length A cosine gamma.
You guys are with me? Now it's correct. let's see. Let's make sure.
All right, go through this, and then when he derived this, I mean, he only took about 7 minutes to reach here. And he actually, you know, if you spend time on this, then you understand projections and dot product very well. So I'm going to stop now. So you realize that that in the lectures, what I'm going to do is this. In the lectures, I'm going to only to highlight the interesting things for you, and that the slides given to you and the videos given to you are more than enough. So I'm going to show you my other slides that I've shared with you, which is 6.0 reference materials. So as I was preparing this last year, I watched many videos in the world offering linear algebra. And linear algebra is a very old course, old as in maybe at least 20, 30 years old for undergraduate. So there are many of them. And I personally like the strength 18.06. So there's strength here. 18.06 is the undergraduate course for linear algebra, and this was recorded about 11 years ago. Some may like Khan Academy, so it's fine. And 3 blue and 1 brown, I introduced you to my during my tutorial, which basically gives a very visual representation of linear algebra, and Math the Beautiful, and Bassett, and many others. So, but if you like work examples, then you see Patrick GMT. Now, there are many books available to you, so don't buy any books. They are free, of course, and you can just check any one of them. The only problem is that if you pick the wrong book, then it might be too difficult or too easy. So the book that we are using very closely is Lay's 5th edition. So I'll zoom. Let's get layout. Lay Linear Algebra 5E means 5th edition. You can pick up this book if you want to. And we are going to cover from this book. Which chapters? So now I would show you, this is Lay's. So this is Lay's content. Basically, we did chapter 1, I guess, part of chapter 2, chapter 3, chapter 4, and we are going to do chapter 6 first, followed by chapter 5. So orthogonality and least squares is chapter 6 in Lay's 5th edition, and then in our chapter 8, we call it eigenvalue and eigenvectors. So we're covering these 2 chapters, almost about 120 pages of it. Okay, then the rest we're not going to cover. All right, so in this course, we have covered chapter 1 to chapter 6 in Lay's book. Right, so let's come back. So as long as you look at the content of the chapters and map it to whichever book you like, it doesn't matter. They are, I mean, in some ways, they are the same. It's just that they would focus on different aspects of it if they are undergraduate. So don't pick up a graduate textbook for linear algebra. You'll not be the same. Don't also pick up a math book, as in a math major book for linear algebra. It might be too abstract, okay, because we are engineering. Now, so some students also ask me about practice questions. There are plenty. So you can see the past year exam questions from MIT, from Yotsumura, from Lay's examples, from anywhere you want. They're more than enough to cover anything you want to practice. Okay, but we do actually give you a lot of questions in the tutorials, so they should be enough. Right, so these are examples all from MIT and others, Medium and things like that. Now this one, okay, so if you ever have a chance and want to look at the more advanced version of 18.06, so they call it 18.065. So this is the master's level course offered 3 years ago by Strang in MIT. Right, so I think now, so what I need you to cover in this 1.5 weeks, 3 hours, is all this 6.1 to 6.3. Okay, and you should be able to watch all the videos within 2 hours, 2.5 hours of all this. So on Friday, so we expect you to be able to finish by this on today, by this on Friday, and by this on next Monday. So that's the speed we are going, and it is very fast. Okay, so if you maybe the speed that we are going is about 3 times faster than what you do in A levels. Okay, so I'll stop now, and then maybe I'll take some questions first.